Imagine for a moment you're on the edge of the unknown, about to step into a black hole. What happens next? Black holes, those enigmatic whirlpools in the fabric of space-time, have long captivated both the scientific community and pop culture aficionados. Often depicted as cosmic vacuum cleaners or portals to other dimensions, these celestial phenomena are surrounded by a plethora of myths. Yet, their true nature is far more fascinating and complex than any fiction. To understand our journey into a black hole, we first need to grasp what exactly these cosmic giants are. So what is a black hole? Well, in the vast tapestry of the cosmos, black holes are some of the most mysterious and compelling phenomena. Imagine a region in space where gravity pulls so fiercely that nothing, not even particles of light, can escape its grasp. This is the essence of a black hole. To understand a black hole, one must first grasp the concept of the Schwarzschild radius. Named after the physicist Carl Schwarzschild, this is essentially the boundary around the black hole. If any matter or radiation crosses this boundary, known as the event horizon, it is inevitably pulled into the black hole, never to return. The event horizon is like the point of no return. Once crossed, the escape velocity required would exceed the speed of light, which, according to the laws of physics as we understand them, is impossible. But how do these enigmatic features of the universe form? The story begins with stars, much larger than our sun. Throughout their life, these stars fuse hydrogen into heavier elements in their cores. This process releases tremendous energy, which pushes outward and balances the force of gravity pulling inward, maintaining the star's stability. However, as these stars exhaust their nuclear fuel, they lose this outward pressure. The result, a catastrophic collapse under their own gravitational pull. In the most massive stars, this collapse continues until a singularity is formed, a point in space where the density is infinitely high, and the laws of physics as we know them cease to function smoothly. Surrounding this singularity is the event horizon, which marks the birth of the black hole. The intriguing aspect of black holes is not just their ability to warp and bend the fabric of space, but also how they challenge our understanding of physics. They represent the ultimate battle between the forces of gravity and the fundamental structures of matter and energy. With such powerful gravitational forces at play, the structure of black holes presents a fascinating topic for scientists around the world. Now picture this, you're an astronaut venturing close to a black hole. What would you experience? Imagine approaching this cosmic anomaly, a point where space and time warp in unimaginable ways. As you draw nearer, the gravitational pull becomes increasingly powerful and selective. Here, the concept of spaghettification comes into play, a term as whimsical as it is terrifying. Spaghettification occurs because the gravity of a black hole is not uniform. It's much stronger at the closer end of any object falling into it. So, if you were heading feet first into a black hole, the pull on your feet would be significantly stronger than on your head. This difference in force stretches you, elongating your body in a grotesque, spaghetti-like manner. The process is a vivid illustration of tidal forces. These are the same forces that cause the oceans on Earth to ebb and flow, yet magnified to an extreme you can hardly fathom. In the vicinity of a black hole, these forces can vary immensely over just a few feet or even inches. This gradient in gravitational pull tries to stretch you longer while simultaneously squeezing you inward, resulting in an extreme form of compression. This transformation isn't instantaneous, but occurs progressively as you edge closer to the event horizon, the point of no return. The experience, while purely theoretical and hopefully never personally experienced, underscores the ferocious power nature wields in the cosmos. While spaghettification might sound like a strange concept, it's a very real scientific prediction for what happens in the intense gravitational field of a black hole. Crossing the event horizon, you enter a realm where the known laws of physics start to behave in unfamiliar ways. Imagine passing through this invisible boundary surrounding a black hole. It's not marked by a signpost, there are no flashing lights. But once you cross this threshold, the universe as you know it fundamentally changes. As you journey beyond the event horizon, every path you might take, every direction you could possibly explore, ultimately leads toward the center of the black hole, a point known as the singularity. Here the gravitational pull is so intense that it warps space and time to the extreme. In this bizarre region, according to Einstein's theory of general relativity, the very fabric of space and time undergoes a dramatic transformation. Time and space, as we understand them, essentially swap roles. For an observer, from the outside, it would appear as if you are frozen in time, eternally caught at the edge of the event horizon. However, from your perspective, time would seem to rush forward, propelling you inexorably toward the singularity. This swapping of space and time is difficult to fathom. It means that while you can move forward in what appears to be space, you are actually moving deeper into future time segments of the universe. Essentially, moving through space is akin to traveling through time. At this juncture, the concept of time ceases to exist as we understand it. Your watch would tick differently, not because it's broken, but because the intense gravity of the black hole alters the flow of time itself. This effect, known as time dilation, is a direct consequence of the extreme curvature of space-time by the black hole's massive gravitational influence. Inside this event horizon, you're cut off from the rest of the universe, moving inevitably toward a singular destiny. The journey beyond the event horizon isn't just a trip through space, it's a dive into the very depths of time and reality, a profound exploration of nature's ultimate enigma. But the story doesn't end there. Black holes are not just bizarre, they are battlegrounds for physics. Imagine a realm where the usual rules of the universe bend and twist. This is the domain of black holes, and among the most fascinating phenomena associated with them is something called Hawking radiation. Hawking radiation is a theoretical prediction by physicist Stephen Hawking. It proposes that black holes are not completely black, but emit radiation due to quantum mechanical effects near the event horizon, the boundary around a black hole. According to this theory, particle-antiparticle pairs are constantly being created throughout the universe, including at the edge of black holes. Normally, these pairs annihilate each other almost instantaneously, but at the event horizon, one particle can be pulled into the black hole while the other escapes. The escaping particle becomes Hawking radiation. Now, if black holes emit radiation, they must also lose mass. This leads to the possibility that black holes could eventually evaporate entirely over astronomical timescales. This introduces a tantalizing question. What happens to all the information that falls into a black hole? This is the crux of the information paradox. The information paradox poses a serious challenge to physicists. According to the laws of quantum mechanics, information cannot be destroyed. However, if a black hole that has absorbed information eventually evaporates completely, where does the information go? Some theorists propose that the information is somehow encoded in the Hawking radiation, while others suggest it could be trapped at the core of the black hole, or even in another universe. This ongoing debate not only tests the limits of quantum mechanics, but also of general relativity, pushing scientists to consider new, more comprehensive theories of how the universe works. Perhaps it points towards a new theory of quantum gravity, a theory that could unite the very large, general relativity, with the very small, quantum mechanics. The mysteries of black holes push the boundaries of our scientific knowledge and challenge our understanding of the universe. Having journeyed through a black hole, albeit hypothetically, we find ourselves reflecting on the nature of reality and our place within it. Let's revisit the essence of what a black hole truly is, a region in space where the pull of gravity is so intense that nothing, not even light, can escape from it. This gravitational behemoth forms from the remnants of a massive star that has collapsed under its own weight during a supernova explosion. The result is a singularity, an infinitely dense point where all the star's mass is concentrated. Our hypothetical voyage took us across this intense gravitational field, illustrating the immense forces at play as we approach the black hole. The journey wasn't just a straight plunge, it was a spiral descent, orbiting closer and closer to the event horizon, the black hole's point of no return. Once crossed, all paths, all destinies converge inexorably towards the singularity. Within this enigmatic boundary, conventional physics begins to falter. Here we explored the bizarre phenomena that occur when the known laws of physics stretch and warp in extreme environments. We delved into the theoretical oddities and quantum riddles that arise, such as the information paradox and the concept of Hawking radiation, where black holes are theorized to emit radiation due to quantum effects near the event horizon. This journey, though purely theoretical, isn't just about understanding black holes. It's about pushing the limits of our knowledge and imagination. It compels us to question not only the cosmos, but also the fundamental principles that govern it. What does it mean for something to be infinitely dense? How does time dilation occur near such extreme masses? These questions challenge our understanding of the universe and inspire deeper inquiry into the fabric of cosmos. While the reality of falling into a black hole remains purely theoretical and exceedingly unlikely, it offers a profound glimpse into the extremes of our universe, where the fabric of space and time stretches beyond our everyday comprehension.